First, I want to do some very quick heuristics, because like I want to motivate this regularization of optimal transport to the development of computational algorithms. And then I look to the clock, I see how much time I have left, and I try to explain some techniques and like how to formalize those heuristic computations that I'm doing here. Okay? So I know that like there is a lot of people in this room who have worked in this topic. I have 1 hour to try to wrap up entropy regularization of OT. Please raise your hand, make a comment, say, I did it. I'm very happy to write your name in the blackboard. Okay? Thank you very much. So let me see what I'm gonna do. So I have epsilon bigger than 0. So this is a parameter. I have mu and u, probability distributions or probability measures in RD. C is gonna be my cost function. And the problem that I'm interested, so I wanna take the infimum of the integral of the cost that Dario showed in his lecture. So this is a double integral in RD times RD plus epsilon and the entropy, the Shannon entropy. And here I'm integrating with respect to the Lebesgue measure. And I wanna minimize among all couplings pi that has marginals mu and u. So, few important things here. So if you are a physicist, you probably define the Shannon entropy with a minus sign because you like that this function is concave. So if you do this and you are a little bit uncomfortable with this plus, please think that this is a minus minus, because like we, as a mathematicians, we really like to put the plus here because this function is linear in pi, and then I'm adding pi log pi that is strictly convex. So linear plus strictly convex means that like if this minimum exists, it's gonna be unique. So that's the reason what we're gonna do. You like convexity to do this. So and this is one nice feature of this entropy regularization. So like by adding this entropy for epsilon is strictly bigger than 0, we know that our solution is unique. And how you're gonna see in a second, like this solution is also a little bit more regular. So the main motivation, like we are gonna use this problem to develop computational algorithms, and we expect that like if you are able to compute it for epsilon very small, we are gonna reach like the classical solution of optimal transport. So for instance, if the cost function is the distance square, I'm gonna reach like the unique solution that is the Monge minimizer. So I'm gonna keep the cost in a very general way, because like sometimes we wanna think about C as like a distance, so a distance in Euclidean space in such a way that I can have a distance in the space of probability distributions, but like sometimes like C describe, for example, the interaction between particles. So I could choose C to be like Coulomb, so 1 over the distance. And this has a different interpretation. I guess like epsilon in this case, it can really be seen as like a temperature parameter. And you can try to think that like mu and u are like cloud of particles that are repelling each other via the Coulomb interaction. So I want to keep this like a little bit more general because this is easier to move to the quantum setting. Yes?
When you say that you take epsilon small, you expect to retrieve the original problem. For example, in the case where you have the Régnier theorem that holds, do you find the transform also in this case?
So the idea is, so let me repeat what you say. So like when epsilon equals to 0, this is precisely a linear programming. So like when epsilon is small, mathematically, I'm not gonna, so let me try to state this, since we are getting to this. So I have this problem here is a OT epsilon. So I'm minimizing pi, so this is now depending only on mu and u. So like, let me say 2 remarks. So I have that like OT epsilon of mu and u converges to OT0, that is the corresponding problem when epsilon is equals to 0. And these like are real numbers, so I'm telling this a convergence has real numbers, but I have something a little bit stronger that like, if I have a solution of this problem that I'm gonna call pi epsilon, let me call this pi epsilon star, this is going to weakly converge also to a solution pi 0 star of the corresponding problem. I guess this is what you are asking, no? What I'm saying, like if I pick a sequence of minimizers that depends on epsilon, when epsilon goes to 0, this is going to converge if I have the distance square to the Brenier solution because it's unique. So if I'm in the distance without the square, that I don't have uniqueness, so this problem here is going to converge to a solution of my optimal transport problem.
Yeah, there is not necessarily a transport for each epsilon, right? This is a weak star convergence, right, of measures.
So what do you mean there is no transport? That this guy is not concentrated in a map?
No, but then the pi of epsilon is not concentrated on the graph.
There is no change. So let me be, so I have been a little bit sloppy here. So let me do this and then this is going to be clear. So the way that I'm defining here is I'm going to be super precise. So I'm taking a linear coast plus the Shannon entropy. If pi is a function, so if pi is absolutely continuous with respect to the product of Lebesgue measure, and let me be pedagogical and use colors, plus infinite otherwise. So this is the way that I'm going to define the entropy, and I'm going to use this notation to be absolutely continuous. So I choose this formula if pi is absolutely continuous with respect to Lebesgue and plus infinite otherwise. So in particular, the solution that is concentrated in a map given by Monge has plus infinite entropy, so can never be a minimizer of this problem. Okay, so like here what I'm doing, so what I'm doing with this regularization is really like seeking for a solution that is a little bit more regular. And this is the computation that I'm going to do in 1 minute. Okay?
Sorry, for this remark, are you assuming that mu and nu are nice, or like that they have finite entropy maybe, or something?
Exactly. So I would. I wasn't expected to do this. So like since I want to make this problem opposite, so here I'm just doing. I needed to have like, so let me call. I needed to have mu log mu and nu log nu finite. Thank you very much, Dima. I needed to have. I need to have finite entropy to make this. In a sense, I may show this in a second. I was expecting to get this through the computations. Did I answer your question? Yes? So let's try to have like a heuristic approach just to get as quick as possible to the computational algorithms. So heuristic approach. So what I want to do, so I want to treat this problem like a finite dimensional problem, and I want to use like a Lagrangian to reinforce this constraint that pi should have the correct marginals. Yes, sorry.
Can you explain again what pi is? What's pi as an element of pi mu nu?
Of course, I can do. So let me do here on the corner. So what I'm saying is that pi, one way that you could think about this. So suppose that I can, suppose that pi, so here, just to make my life easier. So since I know that the solution of this problem should be a function that is absolutely continuous with respect to Lebesgue. So I know that pi is a function, it's not going to be a measure. So what I'm saying here is that like pi of x and y dy should be mu of x and pi. The x and y should be equal d mu. Okay? In the measure theoretic sense, I'm saying that like the projection in the first coordinate should be equal to mu, and the projection in the second coordinate should be equal to nu. Give me a second that I'm going to write this in a nicer way. Okay? So that's what, so let me write the Lagrangian. So this Lagrangian is going to depend on pi, and it's going to depend in two Lagrangian multipliers that I'm going to call u and v. In first, I'm just going to write integral of c pi, the Shannon entropy, and you are going to see in 1 second why I like this minus 1. And then here, I'm going to write the Lagrangian multipliers in a more general way that I'm writing there. That is basically, I'm going to write like integral of mu, the nu, plus integral of v, the nu, minus double integral of u of x plus v of y d pi x and y. So what I'm doing here, precisely, so what I want to do is, so if pi belongs to this set, this is precisely the definition of this set. Because like if pi belongs to this set, u of x is just a function of x. So if I integrate this guy, it's going to give exactly this person. V of y is a function of y. If I do this, I'm going to get v d nu. So and basically, the way that I'm imposing the Lagrange multipliers, I'm saying, I'm putting this expression if pi belongs to the set of couplings, and is plus infinity otherwise. So I'm penalizing if you are not in this coupling. So I know that this guy is not going to be a competitor. Okay? So if you want to take this as a definition for every function u and b that are continued bounded or continuous and vanish at infinity. Okay? So then we have a Lagrangian. What I'm going to do, so like I want to find the best pi, so assuming that this best pi exists, so let me take just the derivative with respect to pi. So I take the variation with respect to pi. Let's say you can think that you're taking a variation pi delta, pi plus delta chi. So delta bigger than 0 and chi with mean 0. So I still want to remain as a probability. I want to be a probability. Then what I get, so this is linear in pi. So I'm going to get, and I put this equals to 0 because I know that I just need to compute the first order condition because my functional in pi is strictly convex. So this is going to give me my the cost plus epsilon log pi minus 1 plus epsilon minus u minus v. Okay? So I'm taking with chi, so I'm just being a little bit lazy. Instead of writing integral of phi with respect to the chi, I'm doing this automatically, like I was in the final dimensional case. Okay? So what is missing, Natalia? So this is the derivative of the entropy, and that's why I have the minus 1, because here I have minus epsilon plus epsilon. Statically, this is beautiful. I can cancel this guy. So then what we have is like epsilon log of pi is equal to u plus v minus c. So pi is exponential of u plus v minus c divided by epsilon. So this depends on epsilon. So like this is actually a function, because like my entropy depends on x and y. So this is actually a function. This is optimal. This depends on epsilon. So I'm not keeping everywhere the dependence of epsilon, but like also u and v depends on epsilon. And this is something that makes this problem a little bit difficult, but I'm going to drop this epsilon in u like a lot of times. Okay? If you plug this solution into the Lagrangian, and you do the computation, what you are going to get is like what is so-called like the dual formulation of this problem, or like the dual functional. You are going to get like integral of du d mu plus integral of v d nu minus epsilon double integral of exponential u plus v divided by epsilon dx dy. So let me do this. This is integral rd times rd. And this is what I'm going to baptize as the d epsilon of u and v.
Plus epsilon.
This is at u epsilon g epsilon, these specific u's?
Yes, exactly. If I plug this one inside this Lagrangian,
Nice.
this is precisely the guy that I'm going to get.
Yeah, but you are also plugging in that specific u epsilon and specific v epsilon, right?
And I'm plugging exactly this epsilon in this epsilon. Thank you very much, Dima. Yes, I need to put this. Exactly. So this is the epsilon. I told you that I'm going to drop all the time. I already drop in the next line. Thank you very much. Okay. No, I'm wonderful. This is just like to make in a few seconds like both the primal and the dual functional appear. So if I have time in the end, I try to give a more mathematical explanation for this. So what is...
Can I say something maybe?
Of course, Lorenzo, you should interrupt all the time.
In this case, answering also his question, in this case, when you plug pi epsilon exactly that e to the u plus v, if is more like the optimality condition, right? So in that case, if that pi is a probability measure, then the last piece actually disappear even. like happens in duality argument usually. The second piece with epsilon integral of E, blah, blah, if that is the integral of the probability measure, is 1. So you just get minus epsilon, yeah? But the magic that Augusto is saying that this formula, written like this, is going to be true for all U and V, also not the optimal one. Yeah, this is going to be the dual formula.
Exactly. So since this guy is very good, Lorenzo, since this guy is a probability, because I'm taking on pi's that are in particular probability distribution, so this is going to be basically 1. So and then the function will be only this. But this is going to appear in a second.
Then it's true, actually the true formula is, as you say, it's evaluated in UV and then you keep the first two integrals.
Exactly, but like what I'm doing here...
UV, not UV.
Yeah, what
exactly.
So the first two epsilons should be gone, right?
They should, say again, the first...
First two epsilons should be gone.
So this is a function of U and V, right? So like the epsilons of like the optimality condition.
Exactly. So I could define a function. So let's do like this. So if I plug this function, I'm going to get exactly that. But like I could basically say, okay, let me now define for every U and V the dual functional. And I'm defining the dual functional of U and V. Probably this is a nicer way of putting these things. That like when I plug this one, this will be precisely the optimal one. Okay? So then I'm defining the dual functional. Just to what I want to do here like is in a very simple way how to have a relation between this problem that I'm going to call the primal problem and the dual problem. Okay? So since we are talking about this, yes?
Because of the lecture, it's only about half of that board that's visible, or maybe like the bottom third.
Okay, so I'm not going to use this one.
Yes, but maybe the bottom third don't write.
You know, like what is the big problem? Like this part of the board is very challenging for me because I'm very small, so I'm going to just skip this. Okay? But I'm very happy that I can write on the top. No, but thank you, Dima. So let me put some reference here. So like this, like we can look like to Christian Leonard for 2016. If we want to look a little bit like on the convergence, like or more precisely like the gamma convergence of the entropic plans to the solution of like the optimal transport problem. But there is a very nice paper that like has been forgotten for some time that is in the discrete setting, Cominetti and Saint-Martin, that I forgot the year. So, and I needed this just to, that they don't only look in the discrete setting, so up to my knowledge, like are the first people who really have looked on this limit when epsilon goes to 0, and also like in the first order expansion. So what is the error in the first order expansion when epsilon is going to 0? So this is a very nice paper, super nicely written, everything in the discrete setting, and up to my knowledge, like this was the first people to have done it. Okay? So let me see if I need to look on this. So maybe a nice remark, since I have colors. In some talks, or like some people in this audience, sometimes like to write in the Lagrangian an extra condition that is like reinforcing that the pi is a probability distribution. So you could add a new Lagrange multiplier that is like lambda integral of pi dx dy is equal 1, just to reinforce that this is a probability. So this is a little bit redundant, because like if pi has marginals that are probabilities, pi is automatically a probability, but this is super nice, both like from a probabilistic viewpoint or for a computational viewpoint, because here we add a lambda, because now my pi epsilon is not anymore a probability distribution, it's not for free a probability distribution. Now I'm minimizing on the non-negative measures, so this is my domain of pi. But when I choose the pi that make this a probability distribution, I get a dual with a log. That for both the computational reasons, or also like if you want to take a look on the large deviation, this scale makes a lot of sense, because like when epsilon goes to 0, this you can see like has a soft arg mean, and like when epsilon goes to 0, you get precisely what would be the dual problem in the non-regularized case. So I don't want to say a lot about this, but just to point this out, that like makes a lot of sense to look to the dual like on those two formulations. And of course, like at optimal, this guy is going to be 1, this guy is going to be 1, so log of 1 is 0. This is not going to change the value of like the arg max. So what I want to say a little bit more, so probably let me give an example. just to get a little bit a geometric picture what we are doing. So like when we add the channel entropy, physically, we are basically adding the temperature of the system. And it's also a good idea to add the temperature on your life. So I guess no one is gonna argue about this. But like one way of thinking about this is that like, suppose that you are like in the discrete setting. In your distributions, mu and u has all probabilities like 1 over n. So in this case, you know that your solution, so let me here draw the set of pi mu and u, that are the set of coupling. So in this case, you know that the optimal solution when epsilon is equals to 0, so when epsilon equals to 0, is gonna be a map, or more precisely, like it's gonna be a permutation matrix. So what you know is that like your solution is gonna be like in one of the vertex of this polytope that is defined by this set of pi. So as soon as epsilon is bigger than 0, you start to interact a little bit more. So probably you're gonna have like some weight that goes here, but you also interact with your neighbors. And the same like for all the others. And this you can see exactly from this formula here, because like if you are in the discrete setting, pi is a matrix, so then I can use this one. So pi is gonna be a matrix, so this is like pi. I can describe it with I and j. And this formula here is telling me that like every entry of this matrix is an exponential. So this is gonna be EI Vj minus Cij divided by epsilon, so for every I and j, 1n. So this is telling me that I have a matrix, and like while in the classical optimal transport case, almost all entries are 0, but in every row and every column, so a permutation matrix here is a guy that is almost all 0, like this. In this case here, like I'm gonna have also the exponential of something. So I'm gonna have the exponential. So this is gonna be like a non-zero matrix. So while here I have a lot of sparsity, in this case I have 0 sparsity. And that's what I mean, that is a little bit more regular. So if I look in the continuous setting, this is a function. If I look more in the discrete, like I have no sparsity at all. So that is the gain that we are getting with this. And of course, like, so since I'm in this case, so when epsilon is positive, so my solution is gonna be like in the interior of this polytope, and I hope like if I can get epsilon very small in practice, I'm approximating my optimal coupling. So clear this big picture, okay. Just to get a geometric intuition, so what we have here is that there exists a unique solution, so let me write here, there exists a unique solution, pi epsilon, that is given by the exponential of u of x plus v of y minus cx and y divided by epsilon. So now let me talk about two computational algorithms. Yes?
When you look at the Shannon entropy, it's like an anti-method in interior point method, right? But
yeah.
normally you have just a log of the PI if you do linear programming.
Uh-huh.
And you have an interior point method, you would do not a pi log PI, you just have epsilon log PI, right?
Yep. Yeah.
So that's different.
It's a little bit. So this we can discuss a little bit. So I have one of my students, Pavlo. We always argue about this, if this is exactly an interior point method. But like we can discuss about this, I will be very happy. But like it's slightly different of what I have seen. Okay? But I'm happy to learn. So let me do this. So like what we are going to do now. Now, the first algorithm, so this is like one of the reincarnations of Synchorn. algorithm. And the first way that I'm going to talk about the Sinkhorn algorithm is like, has a matrix scaling. So, and what is the idea? So, we are going to take advantage of the shape of the minimizer of this entropic regularization. So, let me write this guy. So, we are going to take advantage that the entropic regularization, I can write it as an exponential of u plus v minus c divided by epsilon, but I can also see this like as a function of a of x exponential of u divided by epsilon, b of y exponential of v divided by epsilon, exponential of minus c divided by epsilon. So epsilon is a parameter that is given, c is a constant that is given, so the only thing that we need to determine to find the optimal pi is to determine a and b. But what we know, this is the optimal solution of the entropic regularization, so in particular, this belongs to the set of couplings, so it's a competitor for the set of couplings. So we basically use this definition and take into account this shape. So if I use this definition, what we have? So this means that a of x, b of y, exponential minus c epsilon, integrating dy, this is going to be mu of x. And if I integrate the same with respect to the x, this is going to be mu of y. So since I'm integrating y and I have a function of x, I can put a outside, so this is going to be a of x, b of y, exponential of minus c divided by epsilon dy. And here I do the same trick with b of y, integrate of a of x, exponential of minus c dx. So if I use those two informations, so let me go back here. Indeed, you see I'm following your advice to use this part. So what we have is, if I try to put this explicitly, so I have a of x is equal mu of x divided by integral of b of y, exponential of minus c divided by epsilon dy, and b of y is going to be mu divided like the corresponding function. So then what is the idea of the Sinkhorn algorithm? So I initialize let's say initialize with a b0, let's say equals to the identity. Then I compute a1 using the b0, and then I compute b1 using the a1. So then like we define the sequence an, bn, in this way for n bigger or equal than 1. Okay, so this is the idea of the matrix scaling. So you can define a stopping time for this algorithm. So for example, the stopping time is when the marginals reach the precision that you want. So you can set up a threshold, 10 at minus 6. Yep.
The 0 is identically 1.
No, you initialize. For example, you initialize with something that is identically to 1, but you can initialize wherever that you want. So for example, if you have any guess what A and B should look like, you start with something very, if you have a good guess, or if you have a warm start or an idea what should be, you can start more like closer to what you expect. No? So then like, so this algorithm is gonna go, so there is a lot of people who have been working on this. Let's make sure that I put the correct reference. So like, Sinkhorn was the first one who proved it convergent, so very likely was not the first one of writing this algorithm, but he was the first one to have a proof of convergence, so that's why he get his name in the Sinkhorn algorithm. So in the continuous setting, so he was writing the, yes. Ah, good. So how now I read the question? I needed to.
They just unmute themselves and ask.
Can you hear me?
Yes. Yes, I can hear you.
Yes. Hi, Augusto.
Hello, I know
so
you.
I have a question.
Wonderful to hear from you.
I know you know. I know you know me. So my question is, so what is the stopping criterion for the algorithm?
So a stopping criteria for the Sinkhorn.
Yes.
So for example, suppose that like now with this algorithm, you can define also what is the pi n, no? I'm sorry that I cannot write the pi n here, so like what is the pi n, for example, you can choose to be the pi n, an, bn, exponential of c, or you can choose like an, bn minus 1, so you have a choice. And then what you can do, like you can compute the marginals of pi n. And you say if the difference of the marginals in your favorite norm or in your favorite divergence is smaller than a threshold that you set up in the beginning, then you stop the algorithm. So I guess this would be like a reasonable way of like getting a stopping time. Of course, you can make the number of iterations, but I guess like the number of iterations is not a good way to compare things. So I guess like a nice stopping time is like define pi n and compute the difference with a metric or a divergence until a threshold that you set up. Did I answer your question? Okay, you hate my answer, so you don't answer anymore.
No, I think he is muted now.
I see. So sorry, Adil, that you are oppressed and they muted you. Okay, anyway. So then, like, just to come back. So Sinkhorn was the first one who proved convergence of this algorithm. So Rusendorf also did a proof in the continuous setting. And more recently, there are two proofs that are very elegant. The first one on Franklin-Lawrence in 95, and another one in the continuous setting, like based on the dynamical formulation by Trifon and collaborators, that like has a very nice geometric, just to say this super quickly, there is a very nice geometric interpretation of this algorithm and why it converges. So like roughly speaking, so you talk to Trifon if you want to know more. So roughly speaking, the idea of the convergence proof like developed by them is that you look for two sets. You look to the sets of planes that has one marginal correct, but the other not. And you look to the other set of planes where it has the other marginal correct, but not the first one. So this set form a cone, and here is when like both marginals are correct. So the idea of their proof is that if you start with a pi 0, so very likely you are not in either of those sets. So at the moment that you do the first iteration, you fix one of the marginals, but not necessarily the other. When you do the second iteration, you fix the other, and you mess a little bit the first one, but you improve a little bit. And more you continue the iteration, you are going to converge to this point here. So more mathematically speaking, so you can define a metric that is a Hilbert metric in this cone. So the Hilbert metric in this cone is the angle. And basically what you are saying is that like the Sinkhorn iteration is a contraction of the cone under this Hilbert metric. And what is very beautiful about this proof is that like since this is a contraction, you can get like almost for free, not only the convergence, but also the rate of convergence of this type of algorithm. So of course, like this is like a general proof that works like for any data. So like you are not getting like the best possible rate of convergence, but like this gives you a proof of convergence and the rate of convergence. Okay, yes?
In the convergence of this algorithm, the convexity of C doesn't play any role, right?
The convex of C does not play any role. So here like C, in theory, like you could say, I want to see measurable, and I just need to assume that mu and nu, that exist like a pi, such that this guy is finite, if you want, to make this problem well posed. So this is very general. Yes?
Let's say I care about pi 0 and I want to take epsilon to 0. Are there ways to choose a good epsilon at each iteration? Like treat this like an interior point?
Okay, this we are going to another realm. So this is less mathematics. So mathematics is beautiful, gamma convergence, things converge. But here now we are dealing with the devil, no? Because like this problem here, when epsilon is equals to 0, is a linear programming that is extremely hard to compute in the sense that it's computationally hard. Now what we are saying, like we are tricking a little bit to say, I'm gonna add the entropy and I'm gonna make this fast. No, I'm trying to trick the devil. And then we do a lot of computations, we are super happy, we get until this point, until we realize that we are dividing by epsilon. And we are dividing something that we divide by epsilon. So this means like if we take epsilon very small, we are taking a division by 0. And that is the price to pay. And like if more epsilon is small, is lower this will be. And very likely, like, there is a point that you should choose how small is the epsilon, because we are going to get like numerical errors. So like we can enter on ways of like cooling down this epsilon during the iterations. We can find the ways of massaging this equation to make this a little bit more robust on the iterations. But I mean, we are moving more like to how can I say, computational tricks and less the theory on this, okay? Like there are some theory on that, but like this we need to look a little bit in details, okay? Just a second, yeah?
Oh, I just wanted to make a remark that we should probably mention that there are still some limitations on the C, so not like with convexity, but we need some either like boundedness or the integrability conditions like C is L1 or Lx or...
So depends, so like yes and no, so we can make this more general, then I'm gonna make more remarks on how general can be C, but like in general, for example, you need the boundedness on C, we need the Lipschitz on C, or you need some strong conditions on the marginals. Like when it happens in the classical case when epsilon equals to 0. No, you can have a C that is very unbounded, but you need to assume that mu and u have finite second moments, so decay a little bit nicely. So it's less about convexity and more about this type of interplay between C, mu, and u, no? Yes, sorry.
Again, it was my question from yesterday. It's again here. There are two cases where either you have a transport map because C is convex and so on, or C is any cost and you don't have necessarily a transport. But for the point of view of computing the value, the Synchron algorithm does a job in any case, right?
Exactly. So because like it's very interesting cases where like C is not concentrated on a map. So there are situations, for example, in quantum chemistry that like instead of having two, you have finitely many marginals, and you don't expect it to have like a map coupling all those marginals. And like it's very, for me, it's very reasonable to take any C. Of course, if we want to compute the Wasserstein distance, we need to take the L2 or the LP distance where we have convexity, we have the solution of Monge. But like this is much more general than this.
But again, that's why my question yesterday was, what are the fields in science where people use optimal transport as a tool? But the tool has two facets. One facet is computing the value of it. And if you are satisfied with this, like for distance of probability measure, you just want to get the value, right?
The cost, no, the real number, yes?
Or you have also to get the map in some cases. Like for the original transport problem, you don't care about Nanchka-Torowicz, you want the map, right?
Yes.
So what are the problems in quantum where you really want both of them, the value and the map?
We need to discuss this later. So when in the break or during the lunch, I'm very happy to go through this. But like just to say a very quick comment, like probably I can get on this. So you can get an estimator of the map via this type of algorithm. Because like A and B are basically exponential of U and U and V. U and V are Kantorovich potentials. So if you take the gradient of one of those potentials, U and U, that you compute here, you get an estimation what should be your map. So like, it's an estimator. It's not precisely the map, but a good approximation that is given by this entropic regularization.
Since we're having a conversation, I just thought I would mention that Synchron did not invent Synchron's algorithm.
He did a proof of convergence of it, no?
Yeah, he's attributed with the first proof, but it was invented by a Dutch telephone engineer in 1937.
No, that's one. I imagine that this is very, very natural to do. Thank you. But I love this idea that like you give the name of algorithms of people who give the proof of it. I think as a mathematician, like it's very useful. Okay.
Augusto.
Yes.
The first one in a different context was Robert Forte. And I'll mention this also in the Shortly Bridges problem. It was 1935, I think.
Ooh.
Robert Forte. And it was in a continuous setting, completely different. Anyway, it's a long history.
Yes.
So very good. This is a point of view of Synchron. So I'm looking to Synchron as a matrix scaling. And now we have like a different, okay, thank you. I'm hearing you.
Yes. I can hear me in my headset, so it's a bit weird when I talk. I try to be concentrated. So, or maybe I take off my headset. One sec. All right, so my question is, what happens if you let epsilon go to 0 along the Synchron algorithm? Does it converge to like the real plan?
you are saying when you cool down the epsilon. So if I understood correctly, you are saying what happens if I take epsilon is smaller in every iteration?
Yes.
So depends. So I don't have on the top of my head like estimates like how to choose epsilon to cool down. But like this can make your life easier. So you say in the first iterations, I have epsilon. I take epsilon very big, so the iterations are faster. I have less problems on iterate. And then I take epsilon small in the end to get the precision that I want for my plan. But
yes. You remember you said that at optimality, if we let epsilon to 0, then it converges to the real plan, right?
Yep.
So the pi epsilon converges to pi 0. And so my question is whether we can do that, but along the algorithm.
Yes, no, we can do this. People have done it. Don't ask me like a solution how to do this. Like this is like, for me, is more practical than a theory. So I can check on the theory to understand like what are the estimates for epsilon. But like, yes, people do this in practice. And at top of my head, like I cannot tell you like what is the theoretical results that guide you to choose epsilon in a reasonable way. Sorry, Adil. Other questions? So what I want to do this, like I want to try to change a different viewpoint to understand a different type of way of computing, of using the Sinkhorn algorithm that is an equivalent way to motivate a little bit like some challenge that we have on quantum optimal transport. So now I want to think about Sinkhorn algorithm as an alternate maximization. And the idea is like, I can look on this problem as a minimization over the transport plan, or alternatively, I can look to it as a maximization of functions uv that are continuous and bounded. So when I'm taking this, so the dual functional, what we call the dual functional before, dx dy, so I'm going to baptize it as like the soup of d of u and v. And basically, like if I compute the variation, so if now I take a variation, let's say u delta, u plus delta chi, and I take the variation of the dual functional with respect to u and put equals to 0, so I just needed to do a first order analysis, so I have like a linear functions in u, minus epsilon exponential, so like minus strictly concave function. So I just needed to compute the critical points to find the maximizer. So now if I do this computation, so here I really needed to assume that like the entropy is finite. And like for simplicity, let me also assume that mu and u are absolutely continuous with respect to Lebesgue, like to make this computation a little bit simpler. So then what I have is like, I have like mu x chi dx when I do the variation, and then I have integral, so the epsilon falls down, and I have integral of like u v minus c divided by epsilon chi x. So let me do like this, dy chi x dx. That's what I want to do. So basically, since those things are equal to 0, so like this implies that mu of x is going to be integral of u plus v plus c divided by dy. So, and if I put just to make things more explicitly, so this I have like u of x plus v of y minus c that depends on x and y. So I can take u out because I'm integrating dy. So then what we have is like, this implies that exponential of u of x divided by epsilon is equal to mu of x divided by integral of e of v minus c x and y dy. And analogously, if I take the variation with respect to v and put equals to 0, I get the other equation. So I get an equation that is like exponential of v of y divided by epsilon u of y integral of u of x c x and y divided by dx. So, and if you look, like if you identify a and b, like I did before, exponential of u and v, this gives to you exactly the same algorithm. And like one thing that I'm gonna do, so like I'm not gonna do the change of variable a and b, I'm gonna write this system in an equivalent way. So I'm gonna write this guy like u of x is gonna be minus epsilon log of the integral that is in the top with respect to y plus epsilon log of mu of x. So here I really need that mu is a function to write like a mu of x, or at least like I needed to look to this like has the absolutely continuous part with respect to a reference measure. And the same to these guys with respect to the x plus. So this transformation here like has been called, let me put this between parentheses, like the C epsilon transform, because like this is really consistent generally what we do. So this is the V C epsilon transform, and this is the U C epsilon transform, because like this is very consistent for those of you who know, like with the C transform in the case when you have epsilon goes to 0, like because similarly, like when epsilon goes to 0, you recover exactly like the arg max, or like minus, like is the arg mean of C minus V. That is precise like the condition that you get for the definition of C transform. So like, just to make a little break of this stage, so like what we have here, like, so we did the entropy regularization, and we have like two equivalent ways of looking for the Sinkhorn algorithm. One is looking this as a matrix scaling. So I start with a matrix pi 0, and I do iterations to fix the columns and the rows of this matrix until I get convergence. Or I can look equivalently as an alternate maximization of the dual problem. Now, what would be those iterations? Like what I'm basically doing here is like I'm looking to the dual problem, I'm optimizing U, keeping V fixed, and then I optimizing V, keeping U fixed. So what I'm doing, like I'm computing the arg max of D with respect to U, keeping V fixed, and I compute the arg max of V, keeping U fixed in this way. So like those are like two equivalent ways of looking to this problem. And like you decide like what is the point of view that you want to do numerically. This, when you go, just to anticipate what we are going to do after lunch, so like this changes a lot when you are going to the quantum case, because like what I want to try to show like after lunch is that like when you go to quantum case, so here you have an exponential of a function, so, or if you are in the discrete case, so pi is a matrix with index I and j, and basically what you are doing, like this is the exponential entry-wise of your matrix. So in particular, like we are allowed to do this trick of bringing ax and bx outside of the integral, because like exponential of a plus b is the same thing of exponential of a times exponential of b. So as soon as we go to the quantum case, what I'm going to show you that like we have a similar formula for the corresponding entropy regularization, but now we are going to have the exponential of a matrix or the exponential of an operator. And like we cannot anymore apply this matrix scaling trick, or at least like it does not make sense to do this matrix scaling trick unless the two potentials u and v, or a and b, they commute with each other. So, and if you do this, this is going to lead to an algorithm that we are not going to exactly solve this problem. We're going to solve a particular instance on this problem when you have like this commutative. But like this alternate maximization is very general.
If you're doing optimal coupling, right, you can think of it as some kind of a tensor product between left and right, which always makes consistent with these unique, right? So, and it's fine.
So what you are saying, like in the quantum case, very nice. So in the quantum case, so there is a generalization of matrix scaling for tensors and for operators. And the best person in the audience who knows this a lot is Rafael Oliveira. So this you need to, but like the question is, you can do this algorithm, but like the underlying question is, okay, when we are doing operator scaling, is there an underlying variational problem that I'm solving in the same way that we do matrix scaling? You know, I know that the solution here minimizes this function, right?
You completely close the map as a as an element in a bimodule, and then you have left and right multiplications of cubes.
So the operator scaling, the question is a little bit more subtle. I can talk to you before lunch, but this is something that we can point out during the seminar. So you can look to the what is understood by the operator scaling introduced by Gurwitz, right? So the operator scale that we understand, like we can look, it still has an alternate maximization of the dual problem in the quantum setting, but you need to change a little bit like the geometry of the setting that you are minimizing. So there is an underlying, so an underlying variational problem, but like so I tried to mention this after the break. But like for us at least it was not that obvious when we start looking on this. But that's a very good point. So like, so there is so just to repeat, so in the operator case, so there is an equivalent algorithm that is the generalization of the matrix scaling. But at least like for us, it was not like entirely obvious, like what is the relation between operator scaling and quantum optimal transport. And so in another way, but like another way that you can look in the synchron algorithm, this is like a more natural way to go to has an alternate maximization. Sorry, yes.
Go ahead. I have a question about the AX, BY. So in practice, people, they discretize, so it's a vector, right?
Exactly. So this is a sum, this is a vector, and this is a sum, yes.
My question is, in the case where C is a quadratic, like you have a Gaussian for evaluation of the integral, right? So you could imagine that you could work with a function. You could start with a mu of x would be, for example, a function of x. And because then you can evaluate by, because you have an integral, a Gaussian integral to compute. And then there are many algorithms to do that.
Very nice, yeah. Agree. So you are saying like if C, I specialize in the case where I have the distance square, mu and nu are general, that's what you are saying. So there are other types of things that I can look at. Agree. So no, there are many different algorithms. I'm just citing two of them. You can also look to this problem and say, okay, this is a maximization of a function that is concave and is an unconstrained maximization. I could a priori use any first or second order method to solve this problem here. So like there are many things that I'm doing, so I'm just trying to illustrate the two algorithms that is going to be relevant for what we are doing next. No, but I totally agree with you. Thank you for... Yes?
If I'm not mistaken, there's also ways of viewing synchron as a form of like mirror descent or geodesic gradient descent. Do these extend to the quantum case as well, or?
You should talk to Zilin, where Z is. Z, so he's the right person to talk. Yes, you can look to this, so you need to define like a Bregman divergence, and then you can write like this has a gradient descent of the primal problem with respect to this Bregman divergence. Yes. It's not obvious because exponential of matrices are not nice as exponential functions, but like you can say something. And I guess you are in the right problem. You're in the right program, so there is a lot of people here who knows this. Thank you for the questions. So let me say, I have like 20 minutes. Let me try to say a little bit about the theory and like what is the way that we can look into that. So let me see if I needed to cite someone. So then we can look. So let me state a more rigorous theorem to close this. So what I'm gonna do is the following. So like let me do a similar trick, but like without using Lagrangians. So let me start with like this cost of epsilon pi and add the same trick that I did previously. So I add. So this is like C epsilon of pi, or let me write this directly again. So let me start with this problem. So I have integral of C d pi plus the Shannon entropy dx dy. Then I add the Lagrange multiplier. So, but now, instead of optimizing, what I'm going to do the following. So I'm going to take everything that depends on pi, and I'm going to put together. And everything that does not depend on pi, I'm going to leave this out. So this is going to be plus c plus pi, no, plus log pi with an epsilon minus u minus v dx dy. And I guess that's it. I didn't forget anything. I have two things here. I have c should be multiplied by pi. Exactly. Thank you. So I have d pi. Thank you. I have this, c, this minus. Yep, that's perfect. So then what I'm going to do is like have a simple proof. So for what we call...
I see the minus 1. Yeah, log pi minus 1.
Log pi minus 1, exactly. Thank you, Franch. So I have... And pi is here. So u plus v. That was the other mistake that I did. The pi is here. So then what I'm going to do is like... I'm going to just use, if you want, Freshoe-Young inequality. Or if you want, like the relation between the channel entropy and the Gibbs state. So and then what I have, like I have that I don't have like the equality between the primal and dual problem, but I have like an inequality. And what basically I'm using here, like is a very simple inequality that I'm saying like that Ts plus epsilon T log T is bigger or equal than epsilon exponential of minus s divided by epsilon. So that's what I'm using here. So if you want, I'm just using that like the Legendre transform of the channel entropy is given by the Gibbs energy. So and in particular, what I have here is that like if pi belongs to this set, so for any pi in this set, this I'm basically adding 0. Then this means that like this computations holds for any pi, in particular like to the inf of pi that belongs to mu and u. So the same thing here. So this holds for any u and v that are continuous and bounded functions. So in particular, this guy holds for any u and v that are continuous bounded. So what we get is precisely the weak duality sup of the dual functional of u and v. And then like we can a little bit characterize all the solutions. So in here I'm going to put a little bit of hypothesis. And so this was first done by me and Simone Di Marino. I believe was in 2019. So I'm under the same hypothesis. So the only thing that I needed to add here is that like the cost function for like being the setting of this paper is a bounded cost function. Yes?
Goes to R.
Say again, goes to R, exactly, goes to R. So I have too much D, thank you, Diba. So what we have is the following, like the following are equivalent. So the following are equivalent. So the first one is, there exist maximizers U star and V star for the dual problem. I'm going to call star for the one with the sup. The second one, so in here I needed to write, I should have done this remark like up to translations. So in the remark is simply if you have a real number and you do compute the epsilon of u plus a, v minus a, this is the same thing of the value evaluating u and v. So we don't see this much in computational algorithms, but like to prove the existence of maximizer, this is like a technical part because like you needed to get some compactness of the maximizing sequence, but since we have some symmetry, we needed to deal with this symmetry to find the, to apply the direct method to show the existence of the maximizer. You have that like U star, the C epsilon transform is equal to V star. So you can think about this like has a sort of like fixed point. When you apply the sinkhorn algorithm and you converge, you are in a fixed point. And V star, C epsilon, is equal U star. So the third hypothesis, the third equivalent, so the third property, is that like if you define pi epsilon has exponential of U star plus V star minus C divided by epsilon, then this guy has the correct marginals. So this is in particular a competitor. And the 4 point is that if you compute, like I did before informally, the cost of pi star epsilon, this is equal to the dual applied to the potentials U star and V star. So in particular, pi star epsilon is the unique solution of the entropic optimal transport. And I'm going to call this.
Is part one that there's this maximizers or that this particular pair are the maximizers?
So what I'm saying is like, so I didn't prove the existence of the maximizer. So what I'm saying is, if there exist maximizers U star and V star, which is true, in the case when the C is bounded, at least, then everything holds.
But I mean, it's for that specific pair U star, V star. So
No, I'm saying there exist maximizers that I'm calling U star, V star. Okay? So if you want, the idea is, no, I can give the idea. I look if I say how much I can do this. So I say there exist maximizers, I'm calling this couple U star and V star. Because like if U star and V star are maximizers, if I take U star plus A and V star minus A, they are also maximizers. But like what I like about this U star and V star is that like they have this nice property. And this is basically like the way that we handle the symmetry. So we have some a priori estimates to get the compactness of the maximizing sequence that we need. But like we need a little lemma to say, okay, we need to select a star or a bar on this maximizing sequence such that this happens. So let's say this is like a maximizer that I'm fixing this constant A.
it's almost like fixing a probability measure, right? I mean, this rescaling that you need to.
Exactly. It's fixing because then I get a probability. Exactly that. Very good. So you see, like, and the way that we solve this is like basically using the direct method of calculus of variation. So probably I can mention like a little bit the idea of this proof, because like the idea of this proof is basically like something that we can adapt very well on the quantum setting. So like the basic idea, like we have the weak duality. So weak duality means that I don't have the equality, but I have the inequality, which is something that we get almost for free. But like when we get the existence of the maximizer, then this guy, when I plug U and V in the dual, I get the solution pi in the primal, or equivalently, if I plug pi star epsilon, I get the equality. So this means if I have a weak duality plus the existence of the max in the dual problem, I have everything. I have also the existence of the minimum in the primal, and I completely characterize this problem.
Pi star of epsilon doesn't mean it's not the optimal solution of the epsilon problem.
Say again, sorry?
The pi star epsilon is not the optimal value of the epsilon problem.
It is. So what I'm saying here is exactly that. What I'm saying is if I take the maximizers of the dual problem and I define this Gibbs state using U and V star, that are the maximizers of the dual problem, this is exactly the optimizer of the primal. And you see, this is really the interplay between alternate maximization and matrix scaling. Because when I'm doing,
Independent of the value of epsilon. So, I mean, if you know the U star and V star, then all epsilon problem have the same optimal solution. Then, right?
No, what I'm saying, like, fix an epsilon. So giving an epsilon, I have U epsilon and V epsilon that does the job. So, but like, it's not universal in epsilon. For different values of epsilon, I'm gonna have different U and V. So this is something that makes this problem a little bit harder. So we know a little bit more how to deal with this, for example, to do expansions in epsilon and so on. But like, U and V are not universal in epsilon. It depends on epsilon. But what is very nice, like if you find the U epsilon, if you find the U and V, you are basically finding the pi. And this is more or less in the spirit of matrix scaling, you know?
Is there some kind of complementary slackness condition?
So this is like, I guess this is what I'm saying on the complementary slackness. No, I'm saying if I solve the maximum of the primal problem, the dual problem, I get a solution of the primal. So I get the equality here. But you see, like I'm doing this in a little bit. So the idea of this proof is a little bit more direct, like that we have weak duality plus existence of the maximizer, then you get equality. And this for us was very useful. So there are some contexts that we have no access to the equality, but like in the quantum case, we can deal with like weak duality and the existence of the maximizer. So in particular, in this set of like operator scaling that we can talk like during this program.
And sorry, in here you also assume like bounded entropy.
I'm assuming like the marginals.
Yeah.
Have
bounded entropy. Okay.
Yes. So one way of getting rid of this, I didn't want to do like also these different equivalents because like in the quantum we cannot see that. Like in general, like typically what we do is like when we define the Shannon entropy, since we have mu and nu that are given, we normally, instead of defining the Shannon entropy, we define the Kullback-Leibler divergence between pi and the product of mu and nu. And this regularizes a little bit this problem, and I can get rid of it. Because basically I'm saying when this guy degenerates, when this guy is 0, because in the matrix scale, you see that appear log of mu. So when this guy is 0, this guy is not going to see it. So if you choose a different regularization, you can improve. You can get a little bit more regular guys. But like if you are working with the Lebesgue measure, you need to assume this. Yes?
So somehow the key thing here is this fact that the exponential function is the Legendre transform of Shannon, of Shannon entropy. But if you take some other pair of such functions, do you get some similar theory?
So you say I have like a convex function, an integral of a convex function.
So instead of regularizing by entropy, you put some other regularization by some function, right? And then you replace your exponential by the Legendre transform of that.
So, okay, what I have done in the classical case is like if I take a function that is convex, like we use the derivative for simplicity and has like a nice growth at infinity, everything works, but there is a key difference. So if I'm doing a regularization of pi, so I use like, I don't know, phi of pi with dx dy in the continuous setting, I may not always have the existence of the maximizer of the dual problem. But if here I do the smart thing that I was telling before to Rafael, that like I take phi of pi with respect of the product measure, then everything works in exactly the same way. But if you take a function that is not the Shannon entropy, those two problems are not equivalent. So thanks to the Shannon entropy, you can use like the nice properties of log, and you know like the arg mean of both problems are translated one to the other.
You need some structure with respect to addition, like the exponential of the sum as a product.
Exactly. So what I'm saying here, like that the Radon-Nikodym derivative with respect to the Lebesgue measure is equal to this guy. So if I change the regularization, I'm saying the Radon-Nikodym with respect to the product measure is going to be phi, the Legendre transform of phi prime of this guy, no? But here, the fact that I'm regularizing with respect to the product measure is very important. And what is very cool is that like in the quantum setting, and this is something that you guys are welcome to talk to Natalia, Lorenzo about this, like you can do exactly the same. So you can replace the Shannon entropy by the von Neumann entropy, and then you can go like to more general convex functions, and even a little bit less regular. So I try to put a little bit of this in the. So those are things that you guys can chat with each other. So I may stop here, and thank you very much for the questions. Like, I like a lot.